In today's video, we are going to be looking at a concept called average atomic mass, also sometimes just referred to as atomic mass. So to start us off, let's go ahead and review what we know about the mass of an atom right now. So at this point, we've learned about this concept of mass number, and we know that the mass number of an atom is always equal to the number of protons plus the number of neutrons. Both of the proton and the neutron have a relative mass of about 1 AMU. Remember, AMU stands for atomic mass unit. And so those two subatomic particles are going to be the ones that are contributing to the overall mass of the atom. Now, how is the mass number different from the number on the periodic table? Well, when we look at the mass number, remember the mass number has to be rounded to the nearest whole number. So mass numbers are always going to be whole numbers because we can't have part of a proton or part of a neutron, whereas on the periodic table, the number that we see has decimals. And we refer to that number on the periodic table. You can see it referred to in a couple of different ways. A few of the more common ones are the average atomic mass, or even average mass. So we know that the numbers on the periodic table have a decimal, but we haven't learned why those numbers on the periodic table have a decimal. And that's what we're going to be looking at now. Well, that average mass that you see on the periodic table is based on two important factors. The first of which is the abundance of an isotope that exists, and the second is the mass of an isotope that exists. Let's go ahead and remember that an isotope are atoms of the same element with different numbers of neutrons. So we know that we're looking at these two factors of an isotope, the abundance and the mass. But what does that word abundance mean? Well, simply put, abundance is how often the isotope naturally occurs. Things that occur more often in nature are going to have a higher abundance. Things that occur less often in nature are going to have a lower abundance. Now, there are two different types of abundances that you could see in relation to average atomic mass. The first of which is this idea of percent abundance, and the second is this concept of relative abundance. Percent abundance is looking at how many of an isotope we have, how many atoms of a certain isotope do we have, versus how many total atoms exist for that element. So let's all take a minute and let's think about a good example of calculating percent abundance. Hopefully you guys all like to eat M&Ms, so let's think about having a bag of M&Ms. And in that bag of M&Ms, all of the different colors represent different isotopes of M&Ms. I want to figure out what is the percent abundance for my red M&Ms. And when I open the bag and I count them, I see that I have a total of 12 red M&Ms in the bag. And then I count the rest of the M&Ms in the bag, and I see that I have a total of 40 M&Ms. So if I want to calculate the percent abundance of my red M&Ms, I'm going to do 12 divided by 40 times 100. And we're going to get 30% abundance for the red M&Ms in our bag. Well, that percent abundance is also related to the concept of relative abundance. In order to find the relative abundance of an isotope, you're simply going to take that percent abundance and write it as a decimal. The way we do that is we go ahead and divide that percent abundance by 100, which is the same as moving our decimal place 2 places to the left. So our relative abundance of the red M&Ms would be 0.30. Now, when we're solving average atomic mass problems, it's really important to make sure that your abundances are written as a relative abundance, because you're going to take the relative abundance of an isotope and multiply it by its mass. So this is going to be in reference to one individual isotope, for example, carbon-12. And then we're going to do the same for however many isotopes exist of that element. So this would be in relation to our second isotope, maybe for example carbon-13. And we would do this over and over and over again based off of how many isotopes we have. Well, when we add all of those values up, we end up with this concept of average atomic mass. So the two big things we're going to need to calculate the average atomic mass is going to be the relative abundance of an isotope as well as the mass of an individual isotope. Okay, so now that we've learned the formula for average atomic mass, let's go ahead and apply it to this practice problem. So this problem is asking us to calculate the average atomic mass of chlorine given the two isotopes of chlorine below. So let's go ahead and identify a couple of key pieces of information here. So this first one, this idea of chlorine-35 versus chlorine-37. So chlorine-35 and chlorine-37, because these are the whole numbers, this is referring to the mass number of these two isotopes. Next to that mass number, we see this information that the mass of the two isotopes, so for chlorine-35, the mass is 34.969 AMUs, and for chlorine-37, it's 36.966 AMUs. This is referring to the atomic masses of the isotopes because we see those decimals there. And then last piece of information we're given is that chlorine-35 has a percent abundance of 75.77%, and chlorine-37 has a percent abundance of 24.23%. So now that we've identified the key pieces of information, we're going to go ahead and solve for the average atomic mass of chlorine based on these two isotopes. Our first step is going to be converting the percent abundance into relative abundance. And remember, we do that by dividing these percentages by 100. So the relative abundance for chlorine-35 would be 0.7577, and the relative abundance for chlorine-37 would be 0.2423. Now that we have our relative abundances, I'm going to go ahead and label these as well, so we keep all of the information nice and organized. We know that we're going to multiply the relative abundance of an isotope by the isotope's mass. So we're going to take the relative abundance of chlorine-35 and multiply it by the mass of chlorine-35, which is 34.969 AMUs. We're going to do this for however many isotopes are given to us in the problem. Here we have two different isotopes. So I'm going to do the second relative abundance, that 0.2423, and I'm going to multiply that by the atomic mass of chlorine-37, which is 36.966 AMUs. And so when we go ahead and plug this into our calculator, we get an unrounded answer of 35.4528731 AMUs. And the reason that AMU is our unit is that we have AMU plus AMU. And so since the units are the same, they're going to remain just as AMU in our final answer. What we haven't looked at yet is how we would represent significant figures in our answer. Well, if you remember, significant figures always have to come from measurements. Percent abundance and relative abundance, these numbers here, these are not measurements. And so because they are not measurements, they can't be used to determine our significant figures. The only numbers that could be used to determine our significant figures is this idea of atomic mass. So your answer needs to have the same number of significant figures as your atomic masses do given in the problem. So since both of these numbers have 5 significant figures, we're going to go ahead and round our answer to 5 significant figures, and we get a final answer of 35.453 AMUs. The second part of the question asks us if our answer makes sense and why it makes sense. And the answer is that yes, this does make sense because we see that the percent abundance is slightly higher for chlorine 35, so we would expect the average atomic mass to be a little bit closer to the mass of chlorine 35 than to chlorine 37. Remember, a weighted average takes that percent abundance into effect or into account, and so the isotope that has a higher abundance is going to be more represented in the weighted average. So let's go ahead and look at another practice problem. Here we are trying to identify an unknown element referred to as element Q based on the 3 isotopes and the information given about those isotopes in the table. So just like our last practice problem, the first step is going to be taking these percent abundances that we see in the table and converting them into a relative abundance. Remember, we do that by dividing by 100, which is the same as moving our decimal 2 places to the left. So when I divide this by 100, I get 0.9221. When I divide 4.70 by 100, I get 0.0470. And when I divide 3.09 by 100, I get 0.0309. Now we're going to set up the problem just like we did for our determining the average atomic mass of chlorine. We're going to multiply the relative abundance, so 0.9221, by the mass of that isotope. So isotope 28, Q28, has an atomic mass of 27.977 AMUs. And then I'm going to do that for all 3 of the isotopes. And then we plug this into our calculator, and when we put it into our calculator, we end up getting an answer when rounded to the proper number of significant figures of 28.086 AMU. Remember, each of these mass measurements are going to be used to determine our significant figures, and they each have 5 sig figs in them. And so our final answer needs to have 5 significant figures as well. So this is the first answer, is what is the atomic mass of element Q. The second part of the question is asking us to identify element Q and explain our identification. Well, when we take a look at the periodic table, we see that the element that has an atomic mass of 28.086 is actually silicon. And so since this matches the number we see on the periodic table, that is why we would identify this element as silicon. So here's one more practice problem about calculating that average atomic mass. I'm going to go ahead and just walk through solving this problem one more time, and then we will move on to what other things can we do based off of knowing the atomic masses of different elements. So our first step, just like always, is going to be converting to relative abundance if we're given percent abundance. Then we're going to multiply those relative abundances by the mass of the isotopes. We're going to do it for all the isotopes we have. When we plug this into our calculator, we end up getting an average mass of 38.489748 AMUs. And we need to go ahead and round to our sig figs. We take a look at the measurements again. Remember, these are the only measurements. We see that each of these has 5 significant figures. So our answer needs to have 5 significant figures. When we round to 5 sig figs, we get 38.490 AMU. When we're trying to identify this element on the periodic table, this one is not as cut and dry as the last couple of problems where it matched exactly. The closest element on the periodic table with an average mass of 38.490 is going to be that of potassium. Again, it's not a perfect match, but sometimes our numbers aren't quite as pretty as we see them in practice problems. And so we wanted to go ahead and just include this in here to show you that sometimes you are going to have to do your best guess at which one is the closest to identify your unknown element. So why is it important for us to learn about the atomic mass of individual elements? Well, we're going to take a look at an example of how this could be applied. So the first thing we're going to do is identify what is the atomic mass of carbon. And if you were to look on your periodic table, you would see that the atomic mass of carbon is 12.01 AMUs. And what is the atomic mass of oxygen? If we look on the periodic table, we see that it is 16 AMUs. And so if we know the individual atomic masses of individual elements, we can actually take that information and apply it to compounds or to molecules. So we can take these two individual atomic masses and we can actually figure out what is the atomic mass of carbon dioxide. So in order to do that, what's written in blue are going to be the steps that we have to take. So the first step is we have to figure out what is the formula for carbon dioxide, and this is one we should know from biology. The formula is CO2, and so that means that we have one carbon and two oxygens. And so if we're trying to calculate the atomic mass for the whole molecule carbon dioxide, we have to use that formula to help us in our calculation. So since I have one carbon, I'm going to do 12.01 AMUs plus, since I have two oxygens, I'm going to do plus 2 times the atomic mass of oxygen, which was 16 AMUs. And then I simply solve that problem, and I end up getting that the atomic mass of carbon dioxide is 44.01 AMUs. So we can take those average atomic masses of individual elements, and we can actually piece them together to determine the average atomic masses for compounds and molecules. So here we're going to go ahead and practice finding the atomic mass of a compound one more time. Here the compound that we are looking at is this idea of sodium chloride, which is more commonly referred to as table salt. Table salt has a formula of NaCl, so sodium chloride. You're going to go ahead and use your periodic table to determine what the atomic mass or average mass of those two elements are. When we look at the periodic table, we're going to see that sodium has an atomic mass of 22.99 AMUs. We're going to be adding that to chlorine's atomic mass or average mass of 35.45 AMUs. And when we add those together, we get an overall atomic mass for sodium chloride of 58.44 AMUs. And that is it for our average atomic mass video.